Okay, are we recording? Yes. Let's do some work here. Right, so there's two things going on in this plot. In the dash red, we have the buried curvature of the bias bilayer graphene at the K point. And that's plotted on this axis. And then and all these other solid plots are rho cc, K times rho cc, which is K, the momentum, times the occupation probability of the conduction band. And yeah, the reason I'm plotting that is because the formula for the conductivity is basically the product of buried curvature in curly brackets here, that's what that is, times the occupation probability. Integrate that over the whole Brillouin zone. When you go to a continuum, you have, and it's rotationally invariant, you basically just get a factor of K and then 2 pi, but the 2 pi is just factors out. So yeah, it's just K times that. So that's why I've plotted here. And the question is, if you plot the value of the conductivity, which is basically J divided by E, if you plot that as a function of the external bias, you get a plot that looks like this, correct? Like this. It's also all conductivity. I think this guy, yeah, as a function of temperature. Here too, right, so this is all for the same temperature. So these are all the same chemical potential. Our mu is equal to A. Yes, I remember applying the Hall conductivity versus the external bias. And you can see the general behavior, it just, rises maybe linearly but for a bit and then plateaus at about 1.8. This is in units of sigma naught here. And the question is, well, yeah, so these are for different temperatures. So the lightest is low temperature, and we see that as the temperature is, at least at low biases, as the temperature is decreased, the conductivity increases, and the question is why? Well, you can at least see what's happening in terms of this picture here. So yeah, because this is just essentially coming from, each data point is the result of an integral of a product of the dashed line with one of these curves over the whole K space here. And so basically you just need to think about multiplying these two together and integrating. And you can see here, without even understanding what's going on, is that the black curve is going to be give the largest integral because it sort of lines up perfectly with somewhat perfectly with the red curve. And in this picture, that black corresponds to, I don't know, but if I look here, do I even say what they are? Figure 3, figure 4. Figure 4. It doesn't say. Okay, well, that was stupid. Black is 50 Kelvin. Right, so at low temperature, this black curve is basically K times the carrier occupation probability. And it's because it's low temperature, I guess it's all concentrated near the edge of the band, right? So, what's my bias? What is my bias? 100 probably. So we're looking at this curve. Presumably this spikes right at the sort of minimum here, more or less. But as you increase the temperature, the carriers sort of broaden about the minimum, and so you get more carriers out here and more in here. So you get the sort of broadening of the peak, which is fine, but because here we're interested in the Hall conductivity, which is just a product of these two things, this one here is going to lead to the largest indigo probably, right? Yeah, this one's larger over a wider range. And to actually figure out, I guess, which one will be the largest, you actually have to compute the integral. But I mean, we did that, and that's, where's that plot? That's this plot here, and indeed the lightest curve is slightly larger. So I guess I can answer this question. Well, do I already do that? I don't remember. This is the weight function. Right, okay, so that's the answer. Okay. Right, my second question was why does this peak, here, but, and in this plot, it's the same idea, but I'm varying now the chemical potential for a constant temperature. And this plot isn't super meaningful because as you increase the chemical potential, you're changing the density of carriers, so maybe it's not really a fair thing to do. One option would be to divide all of these by the carrier density associated with each chemical potential, but I don't really feel like doing that now. I want to think about this question is where is the Berry curvature maximized? Because I wonder, like, it could just be at the band edge. That's probably the answer. So maybe I should just plot the Berry curvature and the energy bands on the same plot. Let's try that. So plots. Oops. I probably need to sub everything in. I need to sub everything in. So hold on. And all the other stuff. Well, just the bias, the bias. Oop. Okay. That's my first plot. And the second one, I just want to do the Berry curvature again, which I've already done. Somewhere here. Well, I gotta be careful. Be careful though. Okay, now let's. Well, maybe that's. Okay. I should note that I'm plotting. just so I don't forget. What? Here. Should I be concerned that it's negative? Which direct point are they looking at here, right? Probably the key point. So maybe something's wrong because I think my Berry curvature might be the wrong sign. I'm not sure, to be honest. Probably he plotted it at the direct point or at the K point. We should said. Maybe he says in his paper. Which direct point, my guy? That's pretty cool. Figure 2. Which point, my friend? Slightly worried. Maybe I should write this down. I'm not too worried. It just means I'm off by a sign somewhere. But so what to do? What to do? What to do? I'll close this. Right. We were trying to understand where this thing peaks, correct? Right. Omega depends on mu? No, it doesn't. It shouldn't, anyway. Yeah, what the hell? Am I being dumb? It depends only on the bands, right? Okay, well, that was pretty stupid then. Don't need to define it in terms of... I need the bias, correct, but... I don't need a plot or t-plot. Oh. Because I have another one. Looks right. Hmm. I wonder, actually, it probably doesn't change images. What's the red one? Yeah, well, it does kind of move around, but only because the axis is moving. Okay. And it's same. Okay. Oops, I don't know why I was just, that's pretty stupid. The Berry curvature is an intrinsic property of the material. It doesn't depend on temperature or anything like that. Okay. Now, I'm sure the plot's the same, the bias, whatever. I assumed it might be at the band edge, but it doesn't seem to be. It would be cool to kind of vary these. It's something big. Oh, interesting. There is a spike here at the yeah, I mean, it does seem to follow that more or less. It does seem to track the band minimum, so to speak. Roughly, anyways. Exactly, hard to tell. And it starts to get kind of mixed with this sort of decaying part, I guess, such that, you know, there's like a lot of curvature here, I guess. I mean, yeah, there is. It's difficult to separate. Like here, if I go up to something big like 500, there's a lot of curvature here, and so the Berry curvature. And I'm saying curvature in kind of like the calculus sense. Like if I'm just talking about the second derivative of this function, there's a lot of curvature here, even just sort of naively. Like look at it, it changes the most around here, and it changes a lot around here. Here it's like kind of linear, so there isn't much Berry curvature. But then you have these two sort of hot spots at the band edge and at 0. Excuse me. And so as you vary the bias, which sort of evolves the bands in some way, the Berry curvature reflects that, and you know, hot here, but those points sort of merge as you change the bias. Now we want the Berry curvature to be as large as possible. Well, if we want a high Hall conductivity, right? So yes, we want this sort of integral to be as large as possible, But we also, you know, want the Berry curvature to be as large as possible. The most this can be is 1. Well, the most each of these can be is 1 minus 1. In you know, we let's say like in the best case scenario, this is just 1. The whole conduction band's full. Forget about this term. Just think about the conduction band. Let's say this is just 1. Then all we care about is maximizing the Berry curvature. Now, if we look at Riley's result, it seems like it's largest for a small bias. However, we have to remember that this whole thing should be sort of multiplied by a factor of k, because it's circularly symmetric. Okay. Okay. Oh yeah, this does sort of reflect that. It's interesting. Yeah, continuing with that line of thought that we're only really interested in, assuming that we can make rho, basically 1. Let's just assume that. Let's try to plot the Berry curvature for a few different values of the external bias. A few different values of the external bias, all times k too. Yeah, let's do it. Yes, they're all times k. I need to account for the fact that further out, bonus. Okay, I need to change these values. So let's just say a, whatever it is, back to what it's supposed to be. Ooh, no, I don't really want to do that. Go away. So even with even with that factor of k, let's put a factor of a half here. Ooh, yeah, it's just so you kind of want a small bias, seems, but that's not what we saw here, or here, right? This suggests you want to a big bias, but we have to remember, okay, so this is interesting. So yes, in this figure, the Hall conductivity appears to grow with the external bias, but I have to remember that I'm always, because I've set mu equal to A, the chemical potential is increasing along here as well, which may be obscuring the fact, maybe obscuring what's actually going on. Now I've set mu equal to A for good reason, namely that mu is our quasi-Fermi level, which you get if you come in with some photons and excite some carriers, and then you let them sort of quasi-thermally relax without recombination. So you have these like two separate quasi-Fermi, two separate Fermi-Dirac distributions. And if you are, we want to have a strong valley polarization, so we assume we come in at something like h bar omega equals 2a. So excite them up to 2a, or to a, right? Plus minus a, from minus a to plus a. Relax quasi-thermally. That's what our mu is. But we have some freedom. It doesn't have to be exactly that, right? Like we can, like this whole region is probably pretty good. Yeah, so actually mu doesn't have to be equal to A, but it's like roughly there that it would be. So I don't know. Who's that from? Sorry. Yeah. So we do, yeah. We do have a bit of freedom. And then this plot suggests, you want to use quite a small bias because the barrier curvature is quite large. So if we can somehow match up the low temperature and then match up rho cc to get here, we should get a very big response. I mean, it's not going to be huge, right? Like this is roughly 2 times that, which is, good, but it's not going to be life or death, I suppose. Small bias. 50 MeV is small. This plot suggests, oh, I was just noticing that you have like these other 2 peaks, which I guess makes sense if you look at the bands. Right, and we're multiplying by K. But here you have, well, there's this other peak here, which I guess comes from maybe here when it's like, yes, we're multiplying by K, so really it's 0 here, but as soon as you move away, it's quite high curvature, so you get this small spike here. So that's quite interesting. And it's not, is it 0? It is 0 here. Oh yeah, because we're multiplying by K. So yeah, it's not really like, I'm trying to figure out a good plot to make that would sort of remove the importance of this chemical potential here. Carrier density, and yeah, I mean I could just divide by the carrier density. Make a function that does that. Yeah. I'll have all that too. Yeah, I should probably write some of those down because it's quite interesting. Okay, so the berry, let's just say subsection, or is it section? Subsection. Sub. So we can just do without that too, of course. Don't need to go that far. Wow. I mean, yeah, this like really does deviate from Riley's result, and it's kind of interesting. It's also kind of confusing. Maybe a legend. Legend. Oops. Okay. Why the heck do they do that? 0.5 times a plot. Yeah. What the hell? Yeah. Oh god. Can I just develop this whole thing, please? Please? Do, I don't know, fucking 3 decimal places? Yes. Maybe that's too many. Okay. Copy all that. Nice. Oh, god. Begin figure. Vary curvatures. Caption. Vary curvatures for several choices of the external glass. It's too big, so I need to do width. Too many figures. I should change the margins. So, okay, let's write with this. In figure, X. Okay. I think it's a decay point. Several choices of external points. This is annoying. I think I should do like H and stiff. Does this work? Or do I need to use floats? H. Oh. Is that not a command? HT? No, that holds at the top. I don't really want to do that. Do I? What the heck is happening? I didn't even see what that did, so. Why can't the captions just be there? Whatever. It's just right. Figure it out later. I think it's at the key point. Blah, blah, blah. Now, as can be seen, too cliche. Does it increase linearly? Well, we should know actually how it increases. So I did the calculation right here. It's proportional to a squared, presumably, plus a constant. Yeah, honestly, this should be where I plot all that stuff. But anywho, well, it's important, so irrelevant. In this, here we go. Why can't you put text on the same page? Mm-hmm. Yeah. Hmm. In other news, Artemi Panarin may be back. He's day to day. Why did he get changed day to day? Panarin. They know something I don't know. Okay. Okay, anyway. Okay, I'll do that later. What's I doing? Mm-hmm. Well, this is not very well. I ask the band minimum and ask k equals 0. Lots of quotation marks. And then now the Hall conductivity relies on it's just that. Well, it is an integral. It's a good point. It is an integral that matters, not just the maximum. Before I was going on about how I expected the like this guy, the red curve, to give the strongest Hall conductivity, but because it's an integral, it's obviously the area under the curve, which, you know, from this plot, it's not really easy to tell what it is. It is related to the fact that, well, I can integrate it over the Brillouin zone. I know it's not constant. I've tried that before. I've observed that it varies with the external bias. But by how much? I believe this one is more. However, at low biases, all the Berry curvature is concentrated in a small region. Doesn't matter. I don't know. There's some thinking to be done here. Go ahead and compute the valley churn number, and whatever, call that K max. K times, what am I calling, omega CC subs. Let's call it C of K because it's the churn number. I'm integrating backwards. But if we'll do, let's say we're doing, well, I don't know what the right way to think about this. I mean, I'll be able to, True, I need to do in, no. Wait, I can't tell if that worked or not, to be honest. These are impossible to delete because you don't know where they freaking begin and end in that way. No! No, I didn't like that. Okay. Oh, wow. Where's A? Did I do parameters? Where? Oh. Conjugate. What the hell? What's C? Oh, that's why. Okay. CH perhaps? Churn? Churn number? Okay. Actually, it would be interesting to plot this. or n, I don't know, q, I don't know. I don't know if it matters, from 1 to 10. Do, yeah, I should probably do like a size is 10. Churn array matrix, ends up. Okay. God. Yeah, right. So is this the churn number? I do need to be careful, don't I? Yeah, it's pretty small. Should probably be careful. But it's k times it, so it should be fine. One, why not? Two, well, at some point it might drop, so just get a sense of what's happening. It does seem to plateau. Okay, let's do a bit more. Just make it a bit smoother. I don't know what would happen if I do this here. Maybe it'll break. Is this the churn number? Churn number. Logical. Okay, so at 0 it just plummets, which I guess makes sense. Turn number here. 1 over 2 pi times that. Hmm. 2 pi times that. It's pretty distressing that it's so small. 1 over 2 pi times the integral. Yeah, but I don't know. Well, okay. Something doesn't seem quite right about that. Even if I look at this one, which seems old. Hmm. Is that just a coincidence? Because it should be, oh, the factor of 2 pi is already there because of the integral. Okay, so there's no extra 2 pi. There's no extra 2 pi because, what is this, 1.5? So weird. If I go further than that, like 2 or something, at some point it's gonna, start to integrate wrongly, but whatever, wrongly. Hmm. Oh, that would be the same. It really does plateau. Oh, so weird. So weird. Oh, yeah. Sure, why not? Yeah. 1.5. What the heck is that? I mean, if I just do one, right? Wrong size. Interesting. Oof. Okay, I think that's a good place to stop.